Hello everyone, today I'm going to cover the very last chapter for our Calculus 1 course. It's chapter 5, it is about integrals. So first of all, let's recall what we learned on chapter 4 is the last section. I think it's about the antiderivative. So if you have the function f of x, say example, okay, say f of x equal to x squared. Then we talk about something called antiderivative. In other words, we're looking for big f of x. What is big f of x? Is that when you take derivative big f of x, you get x squared. And the answer is 1/3 x cubed. That's what we learned last time. And of course, it's just an example. Okay, check it out. X cubed derivative is 3x squared. 3 going to cancel with 1/3. You got x squared left. Big f of x, derivative is going to be equal to f of x. And the function big f of x right here, we call it what? The antiderivative of the function little f of x. And of course, it's not just one function. You can always add a big constant because what? The derivative of constant is equal to 0 all the time. Now, I'm going to introduce the notation of the antiderivative function. So instead of writing big f of x, we denote it this way. Right? Like a long s of the function f of x dx is big f of x. So big f of x will be denoted this way. This long s notation called the integral of the function f of x and then dx right here. Leibniz notation dx, okay, which is integral of x squared dx in this example, and the answer is 1/3 x cubed plus c. So all I want to bring to you is whenever you guys see this notation, you understand what we are looking for, the antiderivative of whatever the function inside. Okay? How about another example? So integral is no more than antiderivative. We just introduced you guys a new notation. So integral of how about 1 over x out of ink? So use a different marker. Integral of 1 over x dx. What are we looking for? We are looking for a function f of x such that derivative, big f of x, such that the derivative is equal to 1 over x. And we know that the derivative ln of x is 1 over x. So integral of 1 over x dx is ln of x, and then don't forget to plus c. Okay? Again, this is no more than the antiderivative that we learned. We just try to introduce you a new notation called the integral. Okay? And this integral called the indefinite integral. Indefinite integral. Okay? The integral without any boundary, just the integral. And again, one more time, it means nothing other than the antiderivative of whatever the function you have inside. Okay, make sure that everyone get it. Give you another easy example. Integral of cosine of x dx. Now, you don't take the derivative of cosine, okay? You ask yourself, what function, when I take the derivative, equal to cosine? So this cosine right here is your little f of x. And you are looking for big f of x. Equal to what? So big f of x equal to what? What function take the derivative equal to cosine? You know that it's going to be sine of x. Okay? And don't forget to plus c because it's not just a function. It is actually a family of functions. You can add any constant. Sine of x plus 1, sine of x plus 2 when you take the derivative. Sine of x, the derivative is cosine. The constant here, the derivative is equal to 0. So you have the big f of x equal to sine x plus c. And now we try to omit that big f of x. We just say what integral cosine of x dx equal to sine x plus c. And that's good enough. And we all understand it. The whole thing right here is a family of functions. Alright, and that's called the indefinite integral. And actually, whatever I'm showing you right here is on section 5.4. I'm kind of going backward a little from our book's order. Okay? Now, let me talk about definite integral. Let me start with this. let me start with this. Say you have x-axis right here, the y-axis right here, and you have a function f of x in here. Lift the f of x. Okay? And this is point A, this is B. Okay? If in this example I give you the function f is above the x-axis, alright? But later on you can apply the same thing. If it's below the x-axis, it doesn't matter, or mix between a part is above and another part is below, doesn't matter. What if I want to calculate the area bounded by the function f of x, the x-axis, and the two vertical lines x equal to a all the way to x equal to b? This is the area that I can calculate. Okay? It looks nice down here with straight line, it looks nice in here with the vertical line, and then in here with another vertical line. But this is a function with any curve. That's why the function is continuous. Alright, so how do we calculate this area? Using calculus. The idea is this. We're going to chop this region into many, many vertical columns. So in this example, I just say do 4. Okay? And I want to calculate, the idea is what? We're going to calculate one area at a time, in the area one column at a time, and then we add them up. Okay? And if we chop it up finely, that means what? If you chop it up into many, many, many columns, then each column going to kind of look like a rectangle. Okay? And we're going to calculate the area of the rectangle using what? Length times width. However, it's not equal, so we kind of approximating in here. Okay, so let's chop it up into 4. Say n is equal to 4. Okay? In this particular example, n equal to 4. I chop it up into 4. And then I want to calculate the area of one column at a time, from here to here, this column. Let's do approximation. How do I calculate the area of, approximate the area of one column? I assume that it's kind of rectangle, and I'll calculate the width. See, now divided evenly into 4 columns. That's each base right here is delta x, okay? Delta x. And delta x is going to be equal to b minus a divided by 4. Or you can write it divided by n in general. How many columns you have divided by that many. B minus a is that much right here. That the difference between a and b is the total length of that much, and then divided by how many columns you have, you got delta x. Alright. Now I'm going to approximate the area of the first column. Say if I want to use the left bar, you guys see the left bar and the right bar are not of the same height because this is just a curve, okay? So if I use the left bar to approximate the area of the first column, then the actual area that I'm calculating is this much right here, from here to here. Alright, so I'm off a little. And same thing, if I use the left bar for the second column, I'm going to have this, and then left bar for the third column, I'm overestimating a little, and then the fourth, I'm overestimating a little. And if I do it that way, you know this. Left approximation with 4 is equal to what? The first column is delta x times FA. Delta x is right here, the base times f of a right here. This is the height and this is the base. You have the area of the first column. Plus the second column is what? This point right here is going to be at a plus delta x, right? You got a is right here plus delta x is right here. Right. Delta x times f of a plus delta x. Okay? This is a plus delta x. And then we move on to that point right here to calculate the height. This point right here, the height is that much. Okay? This is at the point a plus delta x. And then this is the height, and then time delta x. You have this. And then the third column, the area